Um, we need to be talking about a new topic today, but more important than the new topic, I have this. 1 second, just hold on. Let me connect the. Yeah, it's got connected. Now let's go to the screen. Whiteboard. Can all of you see the whiteboard?
Yes, we can.
Yeah, right. So, but before I begin, first of all, questions from the previous class. Did you follow the logic of immobilization? Both the or any questions? Essentially, as I was going to point out that among other things, the basic equations that we derived also have this pattern, where you can actually think about the normal free enzyme and this, and actually use this V is equal to V max S upon Km plus S at S values going to 0. As S value is going to 0, this approximately becomes Vm by Km into S, which becomes a simple first order reaction kinetics with the this is equal to Ks, right? And so this is the part that I was really talking about. So really, if we can take a sort of if we can take a derivative at S. My goodness, already started this struggle. Just hold on for a minute. आप थोड़ा सा टाइम से आइए ना, है ना? आप जल्दीबाजी ऐसे, हाँ जल्दीबाजी करते हैं. आपने चटनी भी कल नहीं बनाया, मैंने राजमा भिगो दिया है. राजमा बना दीजिएगा, चटनी बना दीजिएगा, है ना? मैं क्लास ले रहा हूँ. Okay, can you hear me? And see the board?
Yes, sir.
Yeah. So essentially what I was saying was a simple point that actually this then fulfills all those requirements of simplifications that we had done. First order kinetic simplification, and the fact that substrate concentrations are close to 0, and then we can obviously use the approximations or the equations that we did last time. So I don't want to sort of get into it, but this is one of the ways that we derive the expressions for this. So shall we? So what is the basic equation? Do you remember your basic equation? What was the equation we derived? So rate was, I hope you remember, the rate for first order kinetics was given with diffusion was essentially 3 by R root dE diffusivity by Ki, and this into K1S, right? K1, or didn't call it K1 CAS, right? Do you remember this expression, which then effectively became obviously 3 by R, and when we take the derivative, obviously let us take the dE K1, we can get the K1 inside, right, into CAS. So derivative of this will be nothing but this expression itself, this alone, and then you set this equal to the. So I hope you can understand this, and this is equal to now your Vmax, and this is the actual experimental data, right? Remember that this is the actual data. This K1 here represents, I hope you're following the argument. This K1 here represents the true Vmax upon Km. This is not Km, but this is equal to Vm by Km apparent into CAS, where this is the measured or the actual measured value. I should not say actual, I should say measured. And this is the true Km. And so you can see that from the Km apparent and the Km true values and how it changes, we can use this equation to find out what is the role of R and D. And if you know R, you can find out D. If you know D and R, then, and if you know Km true, then you can find out Km apparent, and so on and so forth. Are you getting this argument? Vm does not change. So, I mean, between the relationship between Km, the Km apparent, because this reaction will now be like this. This is the true reaction. This is the observed reaction. And so when you take the derivative on this and find this out, and this derivative and this derivative, the difference between these two derivatives is really because of mass transfer impacts. And because this is first order reaction, all our assumptions, the rate equation is perfectly okay. All the assumptions are fine. So we can use this equation, and actually between these two derivatives, we can put them equal, and you can see the relationship between Km and Km apparent. And of course, dE and R. Is this obvious?
Yes, sir.
I think it should be reasonable. I mean, please go back and practice a few experiments. So I will stop here. The only thing I want to say very quickly is that I don't have a book for this. I'll try to locate something which gives this. I mean, you guys can also try to look around immobilized enzyme kinetics, reaction rate, Thiel modulus, stuff like that. And we have already, so maybe we can get something which you can point out to me. I'm trying to look desperately for such things. So external mass transfer, internal mass transfer, and of course the combination, but let us not get into combinations. Let us not make it very difficult. I mean, ideally then, I should bring in reversible reaction and enzyme deactivation and external mass transfer and internal mass transfer all combined together. And, that can become a very tedious algebraic or mathematical exercise. These things have to be done in actual industrial practice because, I hope what we do in industry is we actually have to do this, right? First of all, we have to determine the length that we need to use so that external mass transfer is not rate controlling. As I told you, this column will have a higher conversion rate than this column with the same volume, given the fact that if external mass transfer is rate controlling, because here the velocities are slower and here the velocities are higher. And of course, pressure drops here are higher. And then what we do in industry actually is that there is deactivation taking place, but the impact of deactivation is less because substrate going forward and product. So as you know, that we are trying to bring the product close to equilibrium because, we want full maximum conversion. People are not willing to pay for separating product at a lower stream. So downstream processing steps actually require that P be as close to P equilibrium as possible. So reaction rates are slow. So as this sort of enzyme tends to deactivate inside these beads, we have, so the P becoming less and less. It is not reaching equilibrium. So what we do is actually we set up columns in what is called I don't know. Have you heard of this? It's called the daisy wheel format. So the columns are like this. They're arranged in a daisy wheel, and each column as it were, I'm just saying some practical aspects of enzyme technology so that you understand that it's not just in the air. Each column is then, there is one column of liquid coming in and radiating tubes. A very poor drawing, but anyway, you understand what I'm trying to say. And each tube has a controller, flow controller. So tube number 1, and let me label them like this rather than in a circle. Suppose this is tube number 1. This is 1, 2, 3, 4, and usually 6 or 7 of them, but let us say 4. And tube number 1 is the fresh enzyme column, which has been set up on 0 day. So for 1 week, it will have the highest flow rate, let us say at 100 ml per hour. I'm just putting some numbers to make it easier. Tube number 2 has got 20% deactivated. So to get the same flow rate, we push it at 80 ml per hour. Tube 2 has 80 ml per hour. Tube 3 has 60 ml per hour. And so on and so forth. Of course, these are just random numbers. And this has 40 ml per hour because it has 40% stability. Remember, so the external mass transfer has to be with respect to this 40 ml and not with respect to 100 ml. Because when the enzyme has deactivated down to 40% or 20%, usually the enzyme norm, industry norm, 20%, then only we say we will now throw this away. So this is 1 week old, this is 0 weeks old, this is 1 week old, this is 2 weeks old and 3 weeks old. And on the 4th week, as the month changes, this is now replaced by a fresh column. This column is removed and a fresh column is put in. So this now gets 100 ml per hour. And this is 1 week old, so it becomes 80 ml, this becomes 60 ml, and this becomes 40 ml, and this becomes 100 ml. And so your flow rates are always constant in a continuous system. And your total flow rate is 100 plus 80 plus 60 plus 40. Right? You getting the point? Or am I talking too fast? It's a simple enough logic. Yeah, it's a simple enough logic. These are some practical, interesting aspects of running immobilized columns in an industrial setting. So, you should know that. So, anytime you visit an industry, we put them in a daisy wheel format, different flow rates depending on how old the enzyme is. The oldest enzyme has the lowest flow rate. The newest enzyme has the highest flow rate, and we keep on reducing the flow rate to compensate for the fact that this enzyme has got deactivated. It cannot, now convert as fast, because we want the product output concentrations in all of them to be equal, almost equal, because you cannot compromise on product quality. So we keep this the slowest flow rate, and remember that this slowing down of the flow rate to counter the effect of enzyme deactivation has the negative effect of increasing external mass transfer. So you need to make this column tall enough so that even at 40 ml per hour flow rate, or 1/4 the flow rate, or whatever, when the enzyme is 25% active, even then external mass transfer is not rate controlled. So if you determine a velocity V, which is required to prevent external mass transfer, then you have to design for 4V. This column will be 4V, and so even when you bring it down to 1/4, this is still not external mass transfer controlling, but because enzyme has deactivated, you need to have a lower flow rate, so that all the columns have different flow rates, and then they are sort of swung on the daisy wheel in a rotating fashion, and one column is taken out. So you have to supply only one column a month. You have to supply only one column a month, or one column usually in 2-3 months. And that is why I said we could bring down, in the last class I said we could bring down the cost of enzymatic conversion of fructose to psychose A to B to 15 paisa per, it is not 15 pence per kilogram, it's 15 paisa. Because the enzyme then lasts for, as I said, each column does a conversion in 10 minutes, it lasts for 5 months or 6 months. You really are reusing the enzyme like crazy. So these are some of the advantages of immobilization, as long as you take care about internal mass transfer is taken care of usually by R, because diffusivity you cannot control. So what is the radius you want to use? The smaller the radius, the lesser the internal mass transfer. The smaller the radius, the less tall you can make it because of pressure drop issues and Kármán-Kozlny equation. So these are all trade-offs in a good design. So all the maths that I'm teaching you, really, we should be doing a practical problem of a design problem where we actually design a set of enzyme columns. But I will leave this to you as a interesting, somebody might take it up as a project or your term paper. How do you design? This is really what engineers do. One of the most important thing as good engineers is not to buy technology from abroad, but when you are given this, somebody will come to you and say, I have A to B, this is my enzyme kinetics, this is my reaction rate, this is my immobilization rates. Chemists will tell you what matrices to use and what is the size of matrices, and then you have to sit down and design an actual enzyme plant for conversion. And then these things become very important. So a practical take as well as the theoretical take are both equally important. So as I said, we don't have too much time for this. So I just want you to give a flavor of these issues that face real industrial design problems. And as you realize that there is a huge trade-off. What would you prefer? External mass transfer, pressure drop, internal mass transfer, size of beads, how long you want to keep it, what is the rate of deactivation you can allow, what percentage deactivation you can allow, and what velocities you can go down to. These are all judgmental calls based on mathematical calculations. So you have to also exercise judgment. It's a combination, really. So let us sort of stop it here. If you have a specific question, as a BTech program, we never actually teach these practical things, but we just sort of mention them from time to time so that you understand that whatever equations you are writing has very clear practical implications, and that is why I want to mention it. We are not really going to go into it in detail. We will go into something else. So today we start a new class, a new section, because there are many things, and I will cover some, I will not cover some. I really don't know how much I will be able to cover. Really, it's almost because of the multiple options. Excuse me. Because of the multiple options, really, what I can cover and what I can't cover is really random almost. So I will do something which is, I think, a very interesting thing which biochemists do. Let us get back to the biochemist domain. It's called the King-Altman method. And the reason I'm going to teach you King-Altman method is because biochemists love this method. It is, okay, hold Can you hear me, all of you?
Yes, sir.
It is, I mean, not really that fancy. I hope some of you, yeah, I'm sure you would have done some physics in your kid. You heard of Feynman integrals and Feynman diagrams? These are very fancy quantum mechanics and, you know, quantum electrodynamics and stuff like that. I just heard about it. I mean, and Feynman did this very interesting thing about, you know, some you know, elementary particle. I'm making a very vague statement here, A to B, and then he discovered that if we find out all the paths which it takes from A to B, and we sum up the probabilities of all the paths. Do you remember this? Have you heard of this very interesting thing that Feynman discovered? And then you sum up all the paths that and you sum up all the paths and find out the probability of each and every path, and then sum them up, integrate them, and then you will actually get the probability of transition from A to B. Have you heard this? Feynman integrals. So this is a more complicated, but I'm sure he borrowed it from this King Altman. The idea is that this is a graphical method to solve a set of linear differential equations, which not linear differential equations, linear equations. So linear equations of the form, I mean, remember what we did, right? We had this E, Es, EP, and so on and so forth, EP, EPI, EI, and so on and so forth, EIS. And then I said that essentially E naught is equal to this plus this plus this plus this plus this. And if ES is giving product, then, you know, you can find out ES divided by E naught. And, you know, Vmax is nothing but K cat or K2, we call it, into E naught, E total. What is wrong with this? One of these days this is going to crash. You're still online, right? Vmax is K2 yes. into E total or K2 into E naught. I mean, I keep on using different terms. I hope it doesn't cause confusion. And really, if ES is making the product or EIS is making the product, etc., etc., we simply look at the ratio of, you know, EIS by ES by E naught or E total. And so that was the fractional saturation logic that I taught you. Remember? And one of the ways, when you have very complicated sets of equations, and becomes tedious to actually solve this fractional, because it's actually, as I showed you, we develop a set of linear equations which can be solved algebraically, but biologists find it very difficult to solve linear algebra problems, and they have developed this very interesting technique called the King-Altman method, which is actually a graphical method to solve these problems. And so I will demonstrate this graphical method to you. The logic of this and the variants of this I leave again to you. Somebody might pick it up as a term paper. Okay, hold on before I start this. We have now very practical questions for you. I mean, when do you want the second quiz? When do you want the second quiz? When do you want the? Hello, can you hear me? When do you want the second quiz? When do you want the lab? When do you want the lab mid-sem or minor, lab mid-semester, and when will you submit the term paper? I have to remember the term paper. So these things have to be done now very, very early. All of you guys are getting into tremendous trouble. These are three important things. And of course, you have to submit your lab reports. So, you know, this is getting, you know, all of you then, you know, delay things, and then the pressure becomes too much. So I want these things, at least these two things, to be offline. I mean, in person done. So all of you are back here. Who is the class representative? Devpriya, are you here?
So he isn't here. I guess he's having a bit of a fever.
Okay, one of you take the responsibility. Tell me a date. Monday लैब प्रैक्टिकल के दिन आप लोग ये लैब मिड सेमेस्टर सेकंड क्विज का डेट बता दीजिए, टर्म पेपर जल्दी से जल्दी जमा करिए. आई नो यू लव टू सबमिट इट ऑन 1st of July, बट सॉरी ग्रेड्स चले जाते हैं तब तक. So you know, I would say that even 1st of April is not a good idea, because you know end semester exams have come. So I want, as I said, 15th everything wrapped up, 15th March, all these three things. or 14th March, whatever I told you. I want all these three things wrapped up by 15th March so that you are free and able to prepare for your semester exam. So please give me a date and please do it fast. It's already 11.
Could we like inform you in tomorrow's lab session? Since tomorrow
That is not tomorrow. Today is Friday, so Monday.
So tomorrow is a working day with Monday timetable, I guess.
Oh, so it's Monday timetable. So no classes for me, right? Or you want the lab practicals?
Sir, I was assuming that there'd be a lab session, but if there isn't, then we can inform you on Monday itself.
Yeah. No, you inform me by mail. We can have a lab session, but I won't have my TA because he's not going to be present. So we will have the lab session. We will cancel this lab. We will have the lab session on Monday, the regular lab session. But yeah, let us leave it. So by tomorrow itself, I can join for half an hour, discuss certain old labs, and we will wrap it up. It will just be a discussion, and you can tell me these things tomorrow. By tomorrow, okay?
Fine.
So please tell me tomorrow, because this freedom should not be misused. So really, let us get back to the original problem. The graphical method of determining this, and well, I think the simplest way the way we were taught programming, the person who taught us told us, the only way to learn programming is to actually start writing programs. You learn the language. So similarly, let us actually think of an example. And I think that is the easiest way to do it. And let me pick up a slightly complicated example so that, you understand. And it's actually not complicated. It's exactly the same model. Let me say that somebody was asking me about bi-substrate systems. I will not, if I get the time, I will teach it. E plus A. Right, and let this is EA, okay, and this is what we talk about. But let us now say that we have EA plus B, so bi-substrate, and they attach sequentially, and there are ping pong mechanisms and stuff like that. But you can well imagine that, and this is EAB, right, and then of course EAB. So this is a bi-substrate reaction, A plus B being catalyzed to. Let us say it is also close to equilibrium P plus Q, right? So let us say this is the reaction, and then EAB undergoes some clever transformation into EPQ, which I showed you some biochemistry. I don't understand this. We showed you a nice lecture, MIT lecture, where this lady who was telling you about the fantastic properties of enzymes, and I suppose you can understand them. And then this EPQ. Let us assume, let's go of the two substrates again in a sequential fashion. So it is EQ plus P, and then EQ sort of gives up the E plus Q. Right. So let us take this example, and we want to develop a reaction kinetics scheme. And obviously, as you can see, you can always, knowing K1, K2, etc., the disequilibrium constant, not the K1, K minus 1, and so on and so forth, and K2, K minus 2, and so on and so forth. You can always set up the same saturation equations that I talked about. So it is the same thing, but I thought I would sort of introduce you to the graphical method, which is called the King-Altman. In many ways, once you get used to the graphical method, it's actually simpler. It's easier. So what is the schema here? The scheme is exactly similar to what we did. E going to EA, right? And so E plus A sorry. E plus A. Sorry. What is wrong, man? E plus A going to EA, right? And let me call it. So now, and then EA going to EA plus B going to EAB. Now I will do this, and that's interesting. This right? Now EAB is now having a very simple. Can you hear me, all of you?
Yes, sir.
EPQ. So this is a equilibrium reaction. So let me sort of replace this with something simpler. Okay, let me sort of replace this with, let me call this EAB, EPQ are the same thing. You know, it is some enzyme complex EX. Okay, and now we have here EQ, the next reaction, EQ here, EQ, and what is this? Remember, EQ is EQ plus P, right? And then here E plus Q for all practical purposes is this. Does this make sense?
Yes, sir.
Yeah. So notice that this is very similar. This is very similar to the stuff that I did for the generalized model for. I mean, this is. I mean, for all practical purposes, I could have done the same thing for the what was that? We developed the generalized model. Remember the generalized model we developed for enzyme inhibition kinetics? I mean, let me sort of rub something out. So let me rub this part out, which I mean, we are talking of King-Altman, so you all know that we are talking of the graphical method. Remember that this was a very, very similar and in many ways to this E plus what was it? ES. I mean, I'm just going to write it. What was it? EI and EIS. Remember this? And this was going to give product. So this was E plus B, right? And so again, E plus S. So what I'm going to do is I'm going to write the forward reaction as K1. This is E plus S. So the reaction rate is K1 E into S, right? E into S. Remember, that is how we were solving this. And the backward reaction is K minus 1, sorry, ES. But this is E into S. So this is a second order reaction, and we will reduce this into a pseudo first order reaction with a rate constant K1S. Okay, so all these reactions will be, so notice that this reaction here, the forward reaction here is K1A. The reverse reaction is K minus 1. What about the forward reaction here? The pseudo first order reaction? If this is K2, this is going to be an irritating business. If this is K2, it is K2B, and this is K minus 2. This here, this reaction is, of course, if it is K3, the reverse is K minus 3P. And similarly here, this reaction is K4, but this reaction is K minus 4 into Q. Okay, so all these reactions with rate constants of K1, K minus 1, K2, and so on and so forth, because this is plus S here, and this is plus I here, and this is plus I here, and this is plus S here. So all these reactions that we talk about are either genuine first order reactions or pseudo first order reactions with a rate constant. So whenever we have K1A into B as the reaction rate, we can say that this is some pseudo first order with respect to some K star B, where K star is K1 into B. So we reduce every reaction to a pseudo first order reaction. That's all right? Is this clear?
Yes,
hello,
sir.
can you hear me? Yeah. So now you just say a quick yes, and that makes my life easy because I can't see your faces. Now, so that is always used. First pseudo first order is not a very different. Now we do the following things. Now this is the master diagram. This is the master diagram this is the basic structure. And so the master pattern is rather simple. The master pattern is this. The master pattern is this for both of these, whether it is this or it is this. So let us do this one. We can do this one as well. It hardly matters. This is your master pattern. And so all these, and in the master pattern, or actually network theory, I hope some of you have done networks. Have you done networks, some of you? And this is, I mean, this is actually, I'm teaching this also because some point of time, some point later, you will be sort of working with nodes and edges. These are the nodes and these are the edges. Have you done this? No. Network theory and linear algebra connections. These are the two courses we never learnt in our childhood. We kept on doing differential equations, and I think class 12th students onwards, they should be taught linear algebra and networks rather than integration and silly differential equations, because today the world is much more on this. And as a suggestion to you guys, from a person who has suffered it, you people forget your differential equations. Of course, you need to know some calculus, but get by and learn your linear algebra and networks and graph theory much better. Now, this is not really graph theory, it's a rather simple point. So this is the basic pattern, and therefore this pattern is actually broken up into, let us look at all the incomplete patterns. We are running out of time. Okay, so we'll do it very quickly. This, what else? ये गायब हुआ, ये गायब हुआ. ये गायब हुआ, ये वाला गायब नहीं किया ना, ये ठीक है ना. 4 combinations of this. Now let us concentrate on E. E can be made by these 4 patterns. Look at this one. This E can be made by going from here. This. This is how you can make E. You have to go continuously, right? I hope you remember this. This one, E can be made by this, and this. This is E here. I hope you remember some graph theory or whatever. How do you make this one? This and this. And here, this, and this. I'll just pause for a minute here. Does that make sense?
Yes, sir.
E is here. E is here. So E is here, and these are the 4 ways you can make E. The 4 ways you can make EQ, EA, EX, etc. can also be calculated. Notice that I have put reversible reactions in all of them. So I will try to wrap. I should have done it faster. So now what is E? What is E therefore? E is the first one here, but it has to be done very quickly now. What is this reaction? Backwards. It is K minus 3. It's a nice way of attacking. Can you hear?
Yes, sir, we can.
Yeah. So E is equal to, let us consider this one. This is, come on, tell me. E is equal to, what is one? Number 1, K minus 3P is the pseudo first order. This one is, this is backward, so it is minus K minus 2. Sorry, K minus 2. And this one is again backward, so it's K minus 1. Right? So this plus, now let us come to number 2. This is the other way around now. So EA plus B, so it is K2B, and this is again normal K3 into K3, and then this is again normal. So this is K4. And what about the third one? Plus this is this reaction, which is K4 into these two reactions, which is, I hope I'm not making mistakes, K minus 2 and then K minus 1. And then there's this fourth reaction, which is plus this into this and this. So this is K3 into K4 into this reaction, this forward reaction. Can you, I do not know whether you this is into K1, K minus 1. So 4 reactions, 4 ways of making E. And
so in the first one, it should be K minus 3 into P into K minus 2 into K minus 1, right?
Oh, देखो गलती किया. Sorry, you are right, absolutely right. Somebody is paying attention. Good. Yeah. So I mean, as I said, I was trying to do it too quickly. K minus 1, K3. Okay. Next one, K2B. I'm trying to do it by looking at this screen. So I'm doing it as fast as you people should be doing it. So you should be telling me. Is this okay? The second one. So this was number 1. This was number 2. This was number 3, and this was number 4. So 4 ways to make E. Remember, if some of these pathways did not work, for example, let me stop because we have to stop here. And so you find out E, you find out EA, you find out EQ, you find out EX. And then obviously, I remember the fraction saturation logic. You can then calculate the total amount of enzyme ET as a sum of all these. E plus EQ plus EA, E plus ET plus E plus EA plus EX, which is nothing, plus EQ. Right? And or as I was talking about in this case, E plus ES plus EIS plus EI. And then you can simply find out the fraction saturation for the terms that are going to lead to product. Job done. And that gives you the form of the equation. The problem is, once you know the form of the equation, then the parameters to be determined from the form of the equation have to be done experimentally. But it tells you the algebraic form of the equation, of the kinetic equation. V is what? V is K1AB minus K2PQ, or is it some other form? This is the typical algebraic. Is this the form of these reactions, or does it take some other shape? Is there a K1A term also? Is there a K1B term? Is there a K3P term or a K3Q term, or is there a denominator? Right? These are the questions that become very important. So the form of the equation then allows you to determine the kinetic parameters. You cannot determine kinetic parameters without the form. And the form of the equation is actually derivable from this King-Waltman method. Doesn't really matter K3, K2, K1, etc., etc. You have a P there and a B there and 2 other constants, and divided by the whole total. So obviously you notice that there is a P into B, P term there, there's a B term there. And in the new denominator, you might have a PB term as well. We'll come to that in the next class. But are you getting this argument? Did you get introduced to it? So we'll talk about King-Waltman in more detail later in the next class. We stop here. Any questions? And please remember that what I am doing is actually a graphical method of solving a set of linear equations without actually solving them.
Sir?
Yeah.
Sir, about the submission dates.
हाँ बताइए.
So, sir, when do you want the quiz to be conducted, sir? Before the 15th?
As early as possible, but the whole problem is I have a very simple point. I would conduct it tomorrow if you want it on Saturday. But my problem is I want to conduct it in person. I don't want it to be conducted where people sort of pick up question papers and disappear. And they don't even appear online. And then they say, here is my submission, which is absolutely fine. I would be the first person to say, take the quiz home and solve it and bring it back. But then don't come back with 20 people having wrong answers, and the wrong answers are matching till the 3rd decimal place. कैसे इंजीनियर हैं, कम से कम 2nd decimal place तक wrong answer type करिए, copy करिए. आप लोग 3rd decimal place तक गलत आंसर कॉपी करते हैं. हम लोग इतने खराब नहीं थे. We would copy to the 2nd decimal place. You know, a wrong answer 3rd decimal place tak match kar raha hai. I mean, what the hell is going on? I'm trying to make a joke out of it, but I'm quite angry about it. You know, this is why I don't want online exams. I want you to come in person. Come with your laptops, come with your books. I have no problems. It is an open book exam. I mean, it makes no sense to teach engineering students to try to remember what they have to remember. They have to solve a design problem. They have to use their brains. But then don't expect the answer to be available in one of the pages of the book or in one of the pages of the notes. You have to do it on your own. That is the whole idea. And I want to hold it as early as possible when you guys do not turn around and say, sorry, I was not in person available. Therefore, please take a re-exam. That is precisely what I want to avoid. If you have all onboarded, that is why I wanted your class representative. If you have all onboarded, and if you say, well, or let us say 95% have onboarded, there are 2 or 3 people who are not being able to onboard, who would like to give online, fine. That also is fine. But I want essentially the full majority, 1 or 2 exceptions apart, who have some problems, who can give the exam online simultaneously, but most of you should be here. 95% of you should be here, and I want the exam the second quiz as early as possible, so that you are free and I am free. Let us not have any more. And similarly for the lab minor or mid semester, I want it as early as possible. My requirement is that this exam should be in person. So is this clear?
Yes, sir. Yes, sir.
Oh, is it? What is the time? Sorry, what is the time?
Sir, it's 9:44.
Oh, I thought it was 9:54. Why the hell am I sort of wrapping up the class then? Okay, so then we can sort of continue with this thing, Altman. I was thinking it's 9:54. I am so sorry. The watch was wrong.
Can I just ask about the lab minor?
Same day. Let us combine it. Let us not have it too much.
And also,
same day. Same day. You give 1 hour of lab minor followed by a quiz. The lab minors will be attended by your seniors as well. So 1 hour, 45 minutes, whatever time you want, not more than 1 hour, 45 minutes preferably. Give your lab minor, and then your seniors leave, and then it's followed by the quiz. Let us not, these are very small things,
yes, okay.
1 or 2 questions at the most. Yeah, let us sort of keep it simple. Let us not have, so we block some lecture hall for 1.5 hours, because you have 120 students, so maybe 2 lecture halls.
We should do it on preferably on a Saturday or a Sunday, because then everyone would be free, because we have labs on 4 days of the 5 days of the week, and we have we all have slots from 5 to 6:30 on one day or the other, and then it would be even more complicated with the senior.
तो कल करेंगे नहीं, but ये फिर आप लोगों को आना पड़ेगा. कल आप करेंगे? कल is too early.
Yeah, कल is too early, sir, and वो सर सब लोग onboarded भी नहीं है, तो वो सर 14th के बाद ही सब अवेलेबल होंगे. लाइक 100% अवेलेबिलिटी होगी स्टूडेंट्स की. तो सर 19th या 20th को करा लें सर. 20th संडे है.
20th संडे है या 19th संडे है? संडे को आप लोग आने को तैयार है सब लोग?
हाँ सर, हम लोगों ने फर्स्ट ईयर में भी सर बहुत सारी क्विज दी हैं जो संडे को होती हैं. प्रोफेसर्स को क्विज.
ठीक है. तो वो हॉल मुझे बुक करना पड़ेगा. सैटरडे को नहीं करना चाहते आप लोग, या संडे को करते हैं? चलिए.
तो सर सैटरडे को सर एक और कोर्स में क्विज है, वो बहुत
ठीक है. तो ठीक है, संडे को ठीक है. तो यू सेंड मी अ मेल in specifically in writing, so that I am absolutely sure that all of you, and I have to also ask your senior batch संडे.
हाँ सर.
ठीक है. तो संडे को लैब और सेकंड मिड माइनर का वो सॉरी लैब माइनर, लैब मिड सेमेस्टर एग्जाम and a second quiz. Okay? Both together. What time?
Sir, 11? Any time, sir. देखो सर सब फ्री होंगे.
11 o'clock.
So preferably in the morning, sir.
आप लोग 11 बजे उठ जाते हैं ना?
हाँ सर, 11 बजे तो उठ जाते हैं.
ठीक है. तो और मतलब शाम को आप लोग गायब हो जाते हैं, तो मतलब मॉर्निंग हाफ में करना है, बट इट कैन नॉट बी 8 o'clock, बिकॉज आधे लोग कहेंगे हम उठ नहीं पाए, सॉरी, है ना. तो मैं 11 बजे रखता हूँ. 11 इज अ वेरी गुड टाइम.
ओके सर.
Sure, sir.
11 to 12:30, let us say, wrap it up, right? 45 minutes for this, 45 minutes for the lab quiz, 45 minutes for this minor, right? Or maybe 1 hour, no, 1 hour, no, 45, ठीक है ना? 45 minutes and half an hour with a 15-minute gap.
Sure, sir.
ठीक है ना?
हाँ सर. और सर टर्म पेपर सबमिशन भी फिर सर
तो ठीक है, संडे से पहले आप सबमिट कर दीजिए, नेक्स्ट वीक से पहले. कोई फायदा नहीं है आप लोगों को बहुत टाइम देकर. क्या करेंगे फाइनली? आप वही करेंगे जो आप करना चाहते हैं. कोई मॉडिफिकेशन
पहले बोला था आपने, तो मैंने क्लास को 15th ही बता रखा है टर्म पेपर सबमिशन.
ठीक है, 15th बहुत अच्छी बात है. तो आप लोग करिए ना. वोंग एंड हेन्स का मेथड है. वॉन्ग एंड हेन्स, मैं किंग ऑल्टमैन बता रहा हूँ, वॉन्ग एंड हेन्स का मेथड करिए या इसका लीनियर अलजेब्रा का कैलकुलेशन करिए, कुछ करिए इंटरेस्टिंग ना.
सर
या एज आई सेड,
मैथमेटिकल
do anything nice. मतलब, you know, I mean, you want me to give you individually what projects? You know, modifications to King Alderman. You know,
हाँ सर वो
King
भी आप
Alderman
बता
methods.
सकते हैं सर, वो काफी यूजफुल
मैं आप लोगों को कई सारे टॉपिक्स दे रहा हूँ, इमोबिलाइजेशन दे रहा हूँ, एंजाइम काइनेटिक्स दे रहा हूँ, पिंग पोंग मैकेनिज्म्स, ये जो ए बी के जो ज्वाइनिंग है इसमें पिंग पोंग मैकेनिज्म्स हैं, बहुत सारे इंटरेस्टिंग मैकेनिज्म्स हैं जिनके बारे में आप किंग ऑल्टमैन के थ्रू सॉल्व कर सकते हैं, समझ सकते हैं, है ना. देन देयर आर वेरी कॉम्प्लेक्स, इरिटेटिंग समटाइम्स, Hahnemann and Hankemann algebraic approximations to enzyme kinetics. On the other hand, you can do your biochemistry and talk about protein structure and how to increase the stability of the enzyme. Or you can talk of absolute organic chemistry and talk of binding. The options are just enormous.
Sir, I wanted to ask about like मैं purification and characterization of HPV16 VLP पे काम कर रहा हूँ, तो सर उसके बारे में लिख सकता हूँ?
बहुत क्लेवर हैं आप, हाँ, मतलब जो चीज आप ऑलरेडी कर रहे हैं, ठीक है, लिखिए. एज लॉन्ग एज यू राइट समथिंग मोर एंड अबव देन व्हाट यू आर डूइंग, वर्किंग ऑन. प्यूरिफिकेशन पे लिख रहे हैं तो आप, यू नो, डू समथिंग इंटरेस्टिंग.
तो सर लाइक क्रोमेटोग्राफी के बारे में,
I give you the freedom. Yeah, okay, go ahead and do it.
Okay sir, okay sir.
Okay. So really now, so then we have time. I didn't realize that.
Sir, term paper, can we have the submission before like sir, you said Sunday, you meant 13th or you meant 20th?
Okay, no, I had told you 15th, so let us stick to 15th. 15th बोला था कि 14th बोला था?
Sir 15th बोला था आपने.
हाँ, तो बस इस वीकेंड में आप बैठ के करिए अच्छे से, और 12th और 13th, 14th और 15th में जमा कर दीजिए. So term paper, let us not play around with this.
So we can make it mathematical as well, right?
Absolutely, I would love it if it was mathematical. But वो फिर आप लोग टाइप नहीं कर पाएंगे मैथमेटिकल, ऑल ऑफ यू हैंडल, यू नो, वर्ड में होता नहीं है. Do you know other you know,
so we can use
LaTeX. Yeah.
लेटेक्स में कर लोगे आप लोग? लेटेक्स अगर कर सकते हो तो बहुत अच्छी बात है, अगर नहीं कर सकते हो तो वर्ड में टाइप करके हाथ से इक्वेशंस हाथ से लिख देना. हाँ
सर, हाँ सर, उसमें बस ये थोड़ा टाइम लगेगा.
इंटीग्रेशन ई रेज़ ऑफ एक्स डीएक्स लिखने में वर्ड में बहुत जान निकलती है.
हाँ सर, हाँ सर.
तो इसलिए मैं ये कह रहा हूँ कि अगर आप लेटेक्स आपके पास है तो लेटेक्स चलाइए, या फिर मैं आई एम गिविंग एनफ फ्रीडम कि आप टाइप करिए अपने वर्ड में, इक्वेशंस को पेन से लिख के चिपका दीजिए और उस फोटो ले लीजिए.
ओके सर. तो सर फिर हम दे सकते हैं सर टाइम 19 तक का, क्योंकि सर लोगों को टाइम लगेगा सर, वो क्या कहते हैं, एक तो मैथमेटिकल इक्वेशंस निकाल के इंटरप्रेट करके लिखने में एंड लेटेक्स पे डालने में सर टाइम.
अब ठीक है, 16 मार्च कर देता हूं मैं.
सर
इतने दिनों से आप क्या सोच रहे थे? ये थोड़ा सा कुछ तो टाइम फॉलो करिए ना. मतलब मैं 1-2 दिन दे दूंगा, मतलब ठीक है 15 मार्च आपका ड्यू डेट मैं चेंज नहीं कर रहा हूं, बट आई विल सॉर्ट ऑफ गिव सम काइंड ऑफ लीव टू 16 मार्च, 17 मार्च 1 नंबर काट के, 18 मार्च 2 नंबर काट के, ठीक है ना, 20 से.
तो सर 16 मार्च को मैं कर देता हूं फिर.
तो मैं 16 मार्च तक कोई नंबर नहीं काटूंगा. 15 मार्च आपका ड्यू डेट है, एक दिन आपका डेडलाइन एक्सटेंड हो रहा है, फिर 17 मार्च ऑनवर्ड्स 1 मार्क पर डे.
ओके सर.
समथिंग लाइक दैट, or 2 marks per day, something like that, है ना. So you know, please submit it. मतलब, you know, this is unfair. You know, the more freedom I give, the more you misuse it. Please don't misuse it. Then I can give freedoms as much as possible.
Yes, sir. Yes.
So essentially, now let us get back to the subject. So essentially, you understand what I made all of them as pseudo patterns, and we have a master pattern. So we will actually solve it. We have a master pattern, and as you can see that all of these reactions are written in terms of first order reactions or pseudo, and you know, it has to consist only of lines from the master pattern. And again, you mind, it has to, आप ये नहीं बना सकते, अब ये नहीं बन सकता है, ये नहीं हो सकता है, ठीक है ना, या ये भी नहीं होना चाहिए. So first of all, and it should connect every pair of enzyme, and there should be no closed loops. So this is also incorrect. Closed loops नहीं होंगे, lines will only be from the master pattern, and it should connect every pair of enzyme. So अगर 4 है तो they all should be connected. एक कोई चीज गायब नहीं हो जाना चाहिए. So that is why this thing led you to these 4 formulations. So this is wrong, this is wrong, this is also wrong. Are you getting this point? So there are these three requirements. I should write it down actually. What did I say? Lines from master pattern, lines only from the master pattern, and this is your master pattern from master pattern. You cannot have random lines coming in master pattern or whatever. And what was the second thing? I said every pair, connect every pair, connect every node as it's called, every pair of enzymes or whatever, every pair of enzymes and every pair of enzymes, and also no closed loops. That's obvious. No closed. So ये मैं नहीं करूँगा because this is a very tedious expression. Let us do this one. Okay, and let me sort of make this problem simple and also interesting so that I understand that you are doing it right. I did not say, oh, we have now suddenly run out of time. Okay, let us do this one. The original problem. This क्या था वो non-competitive inhibition था ना? ये competitive जैसा भी करिए आप लोग. E plus S. What was it? K1, K minus 1, ES. ठीक है? And this was E plus P. No feedback. E plus P. Okay, and this was ES plus I, and this was what? K? No, this was K2, and this I will call it K I and K minus I and EIS. Okay. Now there are three enzyme forms here. The three enzyme forms E, ES and EIS. Notice this is also E. ठीक है? आप मुझे बताइए E के क्या होंगे forms? What is the master loop? I hope you realize the master loop is this: E, ES, EIS, ये. This is the master drawing. Do you follow this drawing now?
Yes, sir.
Now, what is E? बताइए. E का क्या क्या वर्जन्स होंगे? E का एक होगा ये और ये. ठीक है? और कोई है E का? और ये. ठीक है? I'm not doing it deliberately. I'm just sort of hoping
you
can
get this graph again.
Sorry?
So the curve from ES to E.
ES to E to same है ना, ये है ना. This is this. So we have this reaction and this reaction also. ES is giving E, but this reaction is irreversible. So जब हम forward जाएंगे तो हम इसको use नहीं कर पाएंगे. अगर ये ऐसा होता तो इसमें एक K2 भी होता, K minus 2 भी होता, लेकिन this is forward backward both. This will run both ways. This will run only this direction. This will run forward backward both. ये है ही नहीं, तो ये कट ऑफ हो जाएगा. तो जब हम ES की बात करेंगे, when we talk of ES, what are the reactions? E का मैंने बात कर दिया, and I will write it later. What about ES? ES is this and this. Okay. Notice this is not there. Notice this fellow is not there for ES. This reaction here is not contributing to EP because it is going to E plus P, but E plus P is not forming ES. Okay, and EIS of course is very obvious. What is EIS? So this and this and this and this. Sorry, yeah, go ahead. So let me write it.
Right.
I think you. Let me write it. Let me write it. Let me write it for E. What is E? K minus I, K minus 1. Oh, this is really problematic. Sorry. Can you hear me?
Yes, sir.
Yeah. So what is E? Tell me what is E? K minus 1, K minus I, K minus 1. Sorry. Right? Plus this. Come on. Nobody is saying anything. K2
Yes, sir.
into K minus I. K minus I, right? K minus I, हाँ, K minus I. ठीक है. ठीक है. So this is what is forming K E. So this is forming E. We have to go from here. This is for, see, this is one E formation, which is this one, right? And so this is one formation, and the other is this formation. So there are two things. You see, this EIS, this is, so this is K minus I, of course, K minus I into K minus 1. And the other is Ki into K2. That is it, right? These are the two ways of forming. This is this one, this set here. This is K2. This is K2.
Yes, sir.
है This is K minus I, and this is K minus 1, and this is K minus I. और तो कोई है नहीं कुछ. ठीक है? Is this all right? अब ES का बताते हैं जल्दी, टाइम हो गया ना, सॉरी, बट एनीवे ES का क्या है? ES और EIS बहुत सिंपल है. ES का क्या है? ES is K1, ES is K1, come on, K1S, K minus I, right? ES is only one, just this one, this and this. ES is just this and this, that is all. ये backward reaction तो है नहीं. तो K1S into Ki, that is it, ES. Okay? आप लोग for इसीलिए मैंने कहा ना लिख के करना पड़ता है. What is EIS?
It's clear, sir.
It's clear, right? What is EIS then? Tell me quickly. एक ये रूट है.
So K1 into Ki.
K1, so K1S.
The K1S into Ki.
No, K1S into
So
Ki
into
I.
Yeah.
ठीक है ना? This backward reaction is not moving here, so that is it. ठीक है? Okay, and so we have E, we have ES, and we have EIS, and job done. So really what we have to find out is, we really are interested in ES upon ET, which is ET is equal to E plus ES plus EIS. And ES then, and then ES is, this is E by ET, and you know that Vmax is equal to K2 ET. And so ET can be written in terms of this. Are you getting this? Sorry. And V is equal to K2 into ES. Right? That you remember, right? We have talked this. We have talked about this. V is equal
Yes.
to K2 into ES. Vmax is equal to K2 into ET. So V by Vmax is equal to ES upon ET. So Vmax into ES upon ET. But that is it.
So sorry for interruption, but like we have another
Sorry.
lecture.
Yeah. Obviously, I want to finish it. Yeah. Bye. Thanks. Thanks a lot. Next class.
Sir,
Thank you, sir.
Yeah.
sir,
Thank
the
you.
quiz marks haven't been released.
हाँ मैं अभी कर रहा हूँ. I'm doing it.
Oh, okay, sir. Okay.
I'm trying to give some marks. I have to pass you guys. Otherwise, I'm in trouble. You know, your mid semester was a disaster, and quiz is not so good either. So I'm trying to think of ways of making the question paper simple enough for you guys to pass. I don't know how. Okay, bye. Thank you.
Thank you, sir. Good afternoon, sir.
Thank you, sir.
Thank you. Thank you.